3. It's called partial derivatives. Partial derivatives. Okay. So let's just recall what it means to be differentiable. Right? What does it mean if you're back in R to R? Right? What does it mean to be differentiable? To be differentiable at some point means what? What does it mean? Who can tell me what differentiability means? Flo, go ahead.
It means that its derivative is continuous.
The derivative is continuous. Well, not exactly.
Okay.
Not exactly. But I'm glad you make a guess. So actually, being differentiable at C actually means that it has a derivative at C, not necessarily that the derivative is continuous. So let's ask. Let me say the question again. What does it mean to have a derivative at C? What does it mean to have a derivative at C? Ella.
To have a slope.
To have a slope. Okay. So to have a slope there. Okay. Right. You have some function, right? And there's a way of getting a slope. Now this is sort of a vague thing to say, because you could well say, well, can't I? What do you mean have a slope? I can get a slope on this function, right? I have a function that has this angle here, which we generally don't say is differentiable. You could say, well, I can get a slope here. I can get lots of slopes here, right? So what do you mean get a slope? And that's why I put in quotes, Laura.
Oh, I wasn't raising my hand.
You weren't raising your hand, but
I can.
Go ahead, say something.
Say, it can't really have a cusp, can it?
Can't have a cusp, a slope, but no cusp. Right, so nothing like this, right? Nothing like this. Can somebody, does anyone, somebody just give me the limit definition? What's the limit definition for a derivative exist? How about you, Sydney? Do you know?
Like the limit as like x approaches c positive equals the limit as x approaches, or of f of x, of f prime of x. What?
F of x plus h.
Oh, like
Minus f of x, right? And then over h.
Very good. Okay, and then in that case, if you're calling that, then I need to adjust this, right? This should be the limit as h approaches 0, and I need to adjust this thing, right? Differentiable at where? H is going to 0. X. I once teased in a previous class by saying that you all have the creative power of an infinite line of monkeys and typewriters. Right? That is that eventually you're going to hit the right answer. Yeah. Right. So yeah. Actually, let me write this in terms of C because that's how it is. Okay. So right, and the picture is right that there's C plus H, right, and you take the difference f of C plus H minus C, right? You take this difference and you divide by this difference, and you get the slope of the line. You get the slope of the line between those 2 points, and then you let the second point tend towards the first point, right? You let the H tend towards 0, right? And it gives you some slope. And this definition prevents things from this from occurring. Okay, so I'm going to change this a little bit. Okay, so I'm going to start rephrasing this in several ways, and it will start looking stranger and stranger, but it will still be the same thing. Okay, so here we go. Let me just rephrase this a little bit. The limit of f of x minus f of c over x minus c as x approaches c, right, exists. Right? Anyone unhappy with that? You guys, does everyone see that this is the same? This is the same thing, right? I'm taking, all I'm doing is saying, instead of calling this thing c plus h, I'm going to call it x, right? I'm going to take f of x minus f of c, divide by the difference, right? Take the difference between these two values, divide by the difference between these two guys, and that's exactly the same thing that I had before. Okay. This is the same thing as saying that there's some number at prime c such that the limit as x approaches c of f of x minus f of c minus f prime c times x minus c, everything over x minus c is 0. Okay. Who can tell me how I got from this one to this one? What did we do? How do we get from this one to this one? From this to this, say. Paul?
You moved f prime c over, so you subtracted it, and then you multiplied it by an x minus c pretty much to keep it as just f minus, or f prime c. And you just set it equal to 0.
Right. So I move this thing to the other side. I've got 0 on the right-hand side. And then I found common denominators and put it as a single fraction. Right. So I'm not doing anything more than elementary school arithmetic. Right. Okay, so these two things are again the same statement. Okay. Okay. Okay, so now I'm going to do the last one. There exists a function r of x such that, let me say it like this, the limit of r of x is 0 as x approaches c, and r of x times x minus c is f of x minus f of c minus f prime c x minus c. What did I do to get from this one to this one? What's the difference between this one and Lily?
Well, since you had 0 at both, you just set them equal to each other and then multiplied by x minus c.
Yeah, all I did is I'm giving this thing a name, r of x. All I'm doing is saying there's some function r of x whose limit is 0, and if you multiply it by x minus c, you get this. Okay, so that's all that's happening. Just gave it a name. Okay. And the last thing I'm going to do is even less of a move. So I'm just going to adjust this. So instead of saying it like this, I'm going to say and f of x f of x equals f of c plus f prime c x minus c plus r of x because it really doesn't justify another move. In this case, all we did was elementary school arithmetic. Right? We just took some terms. We moved these guys over there. Okay. Okay. So this last one is the way I want you to think about the derivative. Okay. This is how I want you to think about the derivative. There's some function r of x so that the limit of r of x is 0, and the function looks like f of c plus this plus r of x times x minus c. Okay. This is how I want you to think about the derivative. This is actually the better way of thinking about the derivative. Okay. Because this is what's going to... Okay. So now let's think about it. Let's think about it. This thing is going to go to 0. Right? This thing is, as x goes to c, this thing goes to 0. In fact, it goes to 0 doubly in a sort of double sense. Right? This thing goes to 0, and this thing goes to 0. Right? It's not just that one factor goes to 0. Both of these factors each head to 0. Okay, so this heads to 0 in a very strong sense. Okay. Now let's think about this thing here. So as x gets close to c, this thing vanishes in a strong way. And so our function looks basically like this. Well, what's this? F of c plus f prime c times x minus c. What is this? Don't blurt it out. F of c, your function, looks like something plus something that vanishes. What is this something? Don't blurt it out, don't blurt it out. Think about it for a minute, and I'll come back to it. Okay, so what is it? You have this function, right? You have this function. Here is c. Here's your original function f of x, right? Here is f of c, right? You have this guy. It's f of c plus f prime c times x minus c. Paul.
Is it like epsilon, or is it going back to the previous definition for a derivative, where it has to be like that?
Yep. Sydney.
It's like the tangent line.
Very good. Very good. Plus 1 for you on the next exam. And maybe I should count it on this exam. Why not? It's a tangent line, right? It's a tangent line, right? It's the line that passes right at time c. What is it? Where is it? It's at f of c. Right? At time c, it takes on the value f of c. It's a line, right? What's its slope? Its slope is f prime c, right? The slope, right? Let's call this, let me rewrite it. F prime c x minus c plus f of c, right? Right? It's a line that passes through f of c at time c, and it has slope f prime c, right? So it's a tangent line. Is that clear to everybody? Ito? Yes? Yeah? Okay. Okay. So, what does differentiability mean? What does differentiability mean? Differentiability, having a derivative at c, means that your function is basically the tangent line. Your function is the tangent line plus something else that vanishes very fast. Okay, in a very specific way. Differentiability means your function is well approximated by a tangent line. and well in the sense that the difference between you and your tangent line vanishes in a very strong way. Okay. That's what differentiability means. Okay. So the question should be at this point, how do we extend this to higher dimensions? How do we extend this to higher dimensions? Right? Because we have functions. Now our functions are on R2. Say, right? Our functions are on R2. What should be our extension? What should differentiability mean? Anyone want to make a guess? What should differentiability mean? You have a function on R2, right? There's some point AB, right? You have your function, the graph of your function is some sort of surface, right? As this is the height, you have Z equals F AB. Okay. Right. What should differentiability mean for higher dimensions? Yeah. Okay. So that'd be a right way. That'd be a good way of thinking. You say, well, I'm going to guess that differentiability ought to mean that if you take a tangent plane, then that tangent plane should well approximate my function in some sense, right? In what sense? It's not going to be. Maybe it's not completely clear yet, but we'll see. So yeah. So that turns out to be the right way. Maybe I should give you a point for that. Okay, so so that's actually the real way of doing the derivative. But to get there, we're going to have to go through some like partial ways, or some half-assed ways of defining the derivative. Pardon me. Yeah, there's got to be a better word. Partial. Okay. So how do we extend the notion, this notion, to functions from Rn to R? Right? For R2, it's going to be a plane. For R, so there's one naive way, okay, which is fix all but one variable. To slice down to one variable calculus. Okay, and this is the notion of partial derivative. Okay, so partial derivative. This is not the real derivative. This is something that we use to get there. So you have some function from Rn into R, and we define these guys, which we write like this. Okay, partial derivative of f with respect to the ith variable. So partial derivative of f with respect to xi. Okay, and notice that we use this curly d rather than the normal d. Okay. If you use the normal d, then it means that there's one variable. If you use the curly d, it means that there's several variables. Okay, so we define the partial derivative of f with respect to xi at x as the limit as h goes to 0 of f of x1, x2, blah, 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 xi plus h, blah, 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 xn minus f of x1, everything over h. So you just do the derivative in the ith variable. That's all you do. You just do your old-fashioned calculus 1 derivative. You add h in the ith variable. You subtract f at the point, right? And you divide by h. Right, so the picture is, right, if this is, say, maybe it's better. Let me say that let's take this at a place A, and I'm going to replace these guys by A's. Okay. A1, A2, AI, AN. Because there's something a little bit disturbing about using xi's for the point that you're differentiating at and xi's for the variable that you're differentiating with respect to. There's something improper about that. It's wrong. Or it's confusing, I think. Okay. So here's this point, A1, B, A1, A2. Okay. We called it AB earlier. Okay. And you have your function, the graph of your function, some sort of surface lying over it, right? Height f of a1, a2. Okay. And let's say that this is the x1 direction, and this is the x2 direction. Let's see. Okay. Then the picture is that if we're taking the partial of f with respect to, say, the second variable of f at a1, a2, what do? We're going to take this a1, a2, and then we're going to add on something to the a2 variable, right? So we add on something to the a2 variable, we get this guy here, right? We get a1, a2 plus h, right? Right. So this thing is perpendicular here. Right? It's parallel to the x2 axis, right? Okay, and then we evaluate, right? We evaluate, we get some height, f of a1, a2 plus h. We take the difference of those heights, right? Take the difference of those heights and divide by the length of the base here, right? And we take the limit as h goes to 0. Okay, so you see what we're doing. All we're doing is we're slicing through our surface, and we're taking the slope of the tangent line along the resulting curve. Right? We're slicing, all we're doing is slicing through here, right? We get some sort of curve like this, and as h goes to 0, we're going to get the slope of the tangent line of that curve. Okay? And if we had gone this way, then it would mean we slice through, we make a plane, like this, and we slice through, and then we get some curve, right? And we're taking the slope of the curve there, right, along that thing. Okay, so those things are the partial derivatives, and as you see, they're just one variable constructions, right? Yeah, Melissa.
So is the partial derivative the plane that slices, or is it the point?
It is this thing will be the slope of the line that you get when you slice through with a plane. Okay. So, right, here's something here. Right. If you're taking the partial with respect to the x, then you're going to make a plane like this, and you're going to slice through it, right? Slice through it like this. You get some curve that passes through f of a1, a2, right? And you're going to now you're back in the one-dimensional world of calculus 1, right? This is your world. You just have this curve, and you're going to find the slope of the tangent line there.
So the actual partial derivative is the slope of the tangent line?
Mm-hmm. Slope of the tangent line of the curve that you get when you slice through it.
Okay.
Okay. And then, partial with respect to x2, I'm going to take my, in this case, my plane is going to be like this, and I'll get a curve like this, right? And I'm going to take the slope of that curve. Okay. Yeah, Peter.
If you put the partial derivatives together for each, would that give you the plane?
What do you mean, put them together?
Like if you had, when they form an intersection, they make like a one level thing. Is that the actual plane that's tangent to the three-dimensional curve?
Not exactly, but very close. Yeah. So. Yeah. Hold on, and we'll. So yes, the partials will determine the tangent plane. The partials will determine the tangent plane, and we'll see how we'll see how very soon. Yeah. So yeah, good. Yeah. The partials describe the tangent plane. Can be used to describe the tangent plane. Okay. So there's other notation. So there's other notation used in both, sometimes in this book and in other books. So some people write it like this. The partial. This is the ith partial. The ith partial of f with respect to a. Right. So instead of writing the partial with respect to xi, some people just write di. That's actually maybe nicer. Sometimes you see this notation, fxi. So f sub xi. Right. If we write something like this, we mean that we take the partial with respect to j first, and then the partial with respect to I afterwards. Okay. And this is usually written d squared dxi dxj f. So notation for higher partials, right? Just like in one variable calculus, you can take a second derivative, right? Here we could take two derivatives, but they could be two different derivatives, right? Partial with respect to x and partial with respect to y. Okay. So when you see something like this, it means you're taking a second derivative. Okay. So for example, if I let f of xy be, say, x cosine y plus y e to the x, take a second and calculate fxy, and take another second and calculate fyx. So this, right, which I should tell you what I mean by that. So this would be, oops, ji. So this is the extension of this notation, right? First you take the partial with respect to j, and then you take the partial with respect to the ith variable. So this one you take partial with respect to x first, and then the partial of that thing with respect to y, and here vice versa.
Can you explain a little bit more?
Yes.
Take the partial.
Yeah. So taking the partial, how do you take the partial, right? Now we've talked all about it. We know what it is, but how do you do it? Well, here's the instruction. You hold everything else still, and you take the derivative in that variable. Right? You pretend everything else is, you hold everything else still, and take the derivative in that variable. Okay. So if I take the partial with respect to x, I hold y still, right? right? I'm cutting a plane through it, right? So that means I'm holding y at some specific value, right? So this is constant, right? And then I differentiate with respect to x. So let's do it together. What happens? What's f sub x? Well, I'm going to differentiate with respect to x, and so what I do, what happens to this thing?
Cosine y.
Yeah, cosine y. Right, because that's, you think of that as a constant. Okay. I differentiate this thing with respect to x, and I get
Y e to the x.
y e to the x, right? Because y is constant, the derivative of e to the x is just e to the x, right? So y e to the x. Okay. Then I'm going to differentiate that thing with respect to y, and I'm going to get negative sine y plus e to the x. Lily?
What happened to that x with the sine y?
Yeah, we're going to be negative x sine y.
Because isn't it still like a constant, even though it's not changing?
So to get the derivative f x y, I'm going to differentiate this thing with respect to y, right? So the derivative of cosine y is negative sine y. The derivative of y e to the x is going to be e to the x.
Oh, so since you're doing x first and then y, you don't go back to the original function?
No.
Oh.
That would be f sub y.
Oh, okay.
Right, that's something else. So I want the mixed partial. I'm going to take the derivative with respect to x first. Here it is. I take the derivative of that with respect to y, and I get this thing. Okay. Okay. You guys do the reverse. Okay. Do this one. Take 1 minute and take the reverse derivatives. Okay, so what's the derivative? What's the partial with respect to y first? What do you got?
Negative x sine y plus e to the x.
And then if you differentiate that in turn with respect to x, you're going to get negative sine y plus e to the x. And you notice something. Yes, Alana?
Oh, I think that was what you were about to say, but is it coincidental that they're equal, or are they supposed to be equal?
They might not be equal.
Okay.
Okay, so they might not be equal. There's a theorem called Clairaut's theorem that says that if f is twice continuously differentiable, then mixed partials are always going to be equal. Okay, and so twice continuously differentiable means that you can go down to the second partials, and all of those guys are continuous functions. Okay, so twice continuously differentiable. So the second derivatives exist, and that's all right. The second derivatives exist and are continuous. So in this case, well, look, the second derivatives exist and are continuous, and so it is no coincidence that they are equal. If you want to see examples where this sort of thing, where the second partials don't exist, there is a book by Gilbaum and Olmsted called Counterexamples in Analysis. And this is sort of like a book of the weird, right? Like a book of strange things that could happen in mathematics if you don't have all the right conditions, right? Like what happens if you don't require something? Well, then in that case you could get things will go bad in this way, and you can have this example, so it's an example of it's sort of like a bestiary, I think. Yeah. I'm sort of hesitating because a friend of mine in college said that it was like mathematical pornography. Yeah. I'm still trying to understand exactly what he meant by that. But yeah. Anyway, so feel free to take a look. Yeah. Okay. 15.4. Tangent planes and linear approximations. Tangent planes and linear approximations. Okay. So yeah. So let's get back to, right, we have some surface, right? We have some surface, right? And there's some point z naught, where z naught, x naught, y naught, z naught, right? So this thing is lying above x naught, y naught, right? And this point is x naught, y naught, z naught, where z naught is f of x naught, y naught, right? And you're wondering about the tangent plane to the surface, right? So you want the tangent plane to the graph of f. I'm going to use this big gamma for graph of f, gamma graph of f, at the point x naught, y naught, z naught. Okay, so let's think about what the equation of the tangent plane is, right? So we know that from our knowledge of planes that it has the tangent plane can be described with the following equation, right? Z minus z naught equals a x minus x naught plus b y minus y naught. Right? That's the for some a, b, and r. Right? This is the equation of a plane passing through x naught, y naught, z naught, and all we need to do is figure out what the a and b are. Right? That will give us, once we do that, then that figures out for us. Right? And so you say, well, if I take y to be y naught, right? If I take y to be y naught, and I look at the line above it, right? I look at the line above it, then the slope of that line is what? The slope of that curve at that point is
the partial derivative.
The partial, right? And so that tells me, right, if I let y be y naught, then I know the slope of the line. That tells me that a is going to be the partial, right? So this is going to be the partial with respect to x at x naught y naught. Right. Partial with respect to x at x naught y naught. Right. If I let y, if I fix y at y naught, right? If I fix y at y naught, then I get this line, right? Z is going to be, a of x minus x naught plus z naught, right? And what's the slope of the line? The slope of the line is going to be the partial with respect to x. Similarly, b is going to be the partial with respect to y, right? And so the tangent plane, as Peter was seeing, is determined by the two partials. Right, so z minus z naught equals f of x, x naught, y naught, plus f sub y, x naught, y naught, oops, x minus x naught, plus f sub y, x naught, y naught. So this thing is it. It's the tangent plane.
So it only takes two tangent lines to make a tangent plane.
Yeah, right. Because if you know, like, if you're given any plane, and you know two lines on that plane, well, that will give you the plane. Right? That basically fixes the plane. It couldn't be anything else. So yeah, you could rewrite this. Yeah, no, let's keep it like that. So we call. So let me rewrite. So again, we're going to play the game of rewriting. Says that z is going to be f of x naught x. I'm sorry, f sub x. X naught, y naught, x minus x naught, plus f sub y, x naught, y naught, y minus y naught, plus z naught, right? Z naught, which is f of x naught, y naught. Right? Is the equation for the tangent. We call L x y. Let me call this right hand as LXY. So again, f of x. We call this thing the linearization of f at x naught y naught. Probably it's more accurate to call it like a planarization, right? You're getting a function.
Before you rewrote it, that z, and then you just replaced the z with Lx.
Yeah, so what's the difference? What's the difference? This thing here is the equation for the tangent plane. This thing here is the equation for the tangent plane. Okay. This thing here is a function, okay, whose graph is the tangent plane. Okay. This thing here is the tangent plane, right? you're looking at x. This is the equation for the tangent plane. You want x, y, and z that satisfy this. Okay. This thing here is a function is a function on x, y, and the graph of it is the tangent plane. Yeah, thank you for asking. So this thing is the analog of the tangent line, right? This thing is the analog of the tangent line, right? Right. In the one variable case, you have some line. It's going to be f prime c x minus c plus f of c. Right, and you see it's exactly the same sort of thing, right? You have the derivative times some change. You have the derivative times some change plus the value of the function at that point. Okay. Okay. Let me show you. We can actually rewrite this a little bit more. As follows. You can write it like this: L of xy is the matrix f of x, x naught, y naught, f sub y, x naught, y naught, times the vector x minus x naught, y minus y naught, plus f of x naught, y naught. So that brings this thing even more closely in line with the one variable analog. Right? You have the function is the linearization is going to be the derivative. This thing actually is the derivative. Well, it could be the derivative. You have something times the difference plus the value of the function. Okay. And we're going to start off next time. So next time I'll start off explaining this matrix notation and how to make this clear. Okay, that's it for today. I do have